if the report's favorable, then you're allowed to defend. But if you're exactly, so you already know.
Okay, so Tony is guaranteed to finish within 20 minutes. Alternatively, he's going to try and outspeak Adrian Parker, who last gave a talk on the Arabian Peninsula for about 1 hour and 45 minutes. I'm not too sure whether today is the first day we've ever recorded our presentation. Second, is it?
Yeah, we did last week.
So, just for those people that are not familiar, we're actually making this now available. Also, it's just a sort of a reminder that when you ask questions, you're being recorded. So, anyone in the room hasn't heard of this guy at the front, so I am very grateful that Tony stepped forward and gave me a presentation, and thanks very much, Tony. I look forward to learning something about the universe.
Thanks, Tim. How do I start with that? Well, there's one thing, interrupt me. Otherwise, that's going to be a very boring hour and a half. What? No, hopefully it's not going to go for an hour and a half. I don't know. I thought about trying to have something a little broad, especially since my age is the same number now as the answer to the ultimate question of life, universe, and everything. So I thought maybe it was time. And also I realized that since I got here in 2009, I actually never gave a talk since I got the job here. So I think that was because maybe I was scared that people would change their mind and they realized we get hired. I think they thought they hired an igneous petrologist that was supposed to be the new cool car, and I didn't really want to disappoint them. So I tried to stay on the down low for a while. But let's come out, and especially as you get older in the business, it's never your work. It's never just your work that you've done by yourself. Like when you do a PhD, when you present, you've done it. So what I'm going to talk about, it's a whole bunch of things, but a lot of it is Holly's PhD work. And basically what I'm going to talk about inspired Holly's project, and it's probably going to inspire a whole bunch of projects for the next 10 years, if I can. But also there's a whole bunch of people who are listed here who made the project I'm going to talk about possible. And also I can actually thank some GeoQuEST project, not from last year, but from the year before. GeoQuEST was kind enough to give us a little money to fund some of this research, so it's much appreciated. I can't thank the ARC. They gave me a middle finger several times, but that's all right. We've all been there. So yeah, do interrupt me if you have any questions, objections. If you're bored to death and you'd really like me to move on, just let me know. So yeah, I said in the abstract that I wanted to talk about a whole bunch of things. I won't. But what the next Netflix season of seminars basically is going to cover is things like Snowball Earth. So there might be some Star Wars references. But also, not today, but eventually I'll talk about Alexander the Great and more about actually his ancestors and how they affect the environment. I don't think I can promise there's going to be any guest appearances like Colin Farrell or Angelina Jolie. They don't return my calls anymore. And also, eventually, I'll try to talk about heavy metals and the effect on life, the development basically of neurodegenerative disease, but also the development of cancer and also of pathologies, and the effect on how heavy metals, so not these sort of things, although I heard that your brain is bleeding when you headbang, so that could explain a lot of my mental state. Because I used to have long hair like that. So if you're expecting something about Alexander the Great or something about neurogenetic today, you can leave the room, because I'm actually not going to talk about it. What I'm going to talk about, so episode 1, it's probably the worst Star Wars episode, but we should probably start with 1, is the emergence of complex life forms. So why complex life form? Because making life is actually fairly easy. All you need, and Miller and Urey showed that in the 50s. So all you need is some water, some ingredients, some gas, UV light, make a little spark, a little lightning, and you actually produce amino acids. So God, whether it was involved or not, it's actually in nature, it's actually fairly easy, and that won't be surprising at all when we start finding amino acids and all sort of organic compounds on other planets. But so that happened here. So we started making life, and where do we go from there? So there's our tree of life. So Luca here is not an Italian friend, it's our last universal common ancestor. And from here things start branching out into bacteria, archaea, and eukarya. So we start with prokaryotes, so things that don't have a nucleus, so you get basically DNA strand hanging around in the cell. And then from the prokaryote, we started making eukaryotes. So in eukarya here. So the first eukaryotes are fairly simple, so unicellular, okay, just one cell. But they did have a nucleus, and their DNA stacked up in the nucleus. The formation, the emergence of eukarya is quite interesting actually. It's a bit of a Pac-Man story. It's what's called endosymbiosis, where we started, or we had a prokaryotic host cell that, just like Pac-Man, found these little ghosts, a protobacterium, that become the mitochondria that now we have in our cells. So it's sort of little Pac-Man game at the start of evolution that gave us eukaryotes like us, like we know it today. It was quite controversial actually, this theory that doesn't date from 2000. It's actually Margulis, it's actually much earlier than that. That theory came from the 50s or the 60s, I think. And she's a female scientist, and you can imagine trying to put forward a paradigm-shifting theory about evolution as a female in the 1950s. How that must have been fun for her. So then what happens? Okay, so where do we go from there? So we start with eukaryotes, and the oldest fossil, the old evidence for eukaryotes is about 1.2 billion years. Anything older than that is a little shady, and you shouldn't really believe it. And then we see that eukaryotes start to diversify at around 800 million years. So we got 400 billion years, okay? Pretty much the entire Phanerozoic, where nothing happens. So what took so long? Well, if we look at change in ocean chemistry during that time, some people think that, so that's this dark blue here, that the deep ocean was euxinic. So that means that you have no oxygen and a lot of hydrogen sulfide. So basically, you have a horrible smell if you dive in that. That will be smelling like rotten eggs. But much worse, this sort of condition, this sort of euxinic water, that's no good for life. Because when you have sulfides, that's not going to allow for the development of eukaryotes, because the sulfides are going to scavenge elements like molybdenum that are really essential to the development of life. So not ideal conditions for evolution. That's probably why we have this big gap where nothing happens. And when you look, so some people with probably way too much time on their hand start compiling fossil assemblages for the Proterozoic, and what they see is that actually even at 800 million years, so around here, we don't really see to an increase in diversification of eukaryotes. And even during the cryogenian, and I'll talk about that in a little bit, we see a decrease in biodiversity. And it's only at around 650 million years ago that biodiversity is really starting to take off. And remember that, not really a date, but that number of 650 million years. That's what's in red. So where do we go from there? Okay, so we got our first eukaryotes, so our protists. And then we're going to start making simple, what we're going to call simple multicellular eukaryotes, and then from simple to complex eukaryotes. So how do you go, so what I guess I'm interested in is how do you go to something that's relatively simple in terms of life form to what we call complex multicellular eukaryotes, and especially metazoans, so animals. So how do you get to us and other things like cute wombats? I did say I like wombats, did not lie. Or very well behaved cats. She does not drink wine, that's only for us. And more or less cute animals. We were having a nap, quite lovely, lovely koala. So, okay, so what do I mean by complex multicellular eukaryote, by complex life form? So simple eukaryote means that you have every cell in contact with the environment. And that's an example that's not working, but that would be quite fun. You have 4 cells that are just floating around a medium, and that's so that Tetravena socialis. That's the simplest known multicellular eukaryote. So you see, it's a multicellular eukaryote, but it's really not complex. You just have a bunch of cells floating around the medium, and that's about it. What is complex? Well, a few things characterize complex eukaryotes. One thing is cell adhesion. So that basically means what it means. So cells sticking to each other, and that's going to be quite interesting in terms of evolution. So cell developing a membrane and things at the surface of the membrane that allow cells to stick with each other. Another key of complex life is tissue differentiation. Okay, how you go from, well, for instance, what is becoming an industry, how do you go from stem cells, so cells that can be about anything, into mesoderm, endoderm, ectoderm, so into differentiated cells. And another key aspect is 3D organization. Okay? As the organism get more complex and bigger, you're going to have problems to transport things like oxygen, nutrient, signaling molecules. So you need structures that go around the problem of transport when you have a big organism. Okay, in small organism, you have oxygen moving around, for instance, by diffusion. Well, as you get bigger, you need to find ways around that. So complex. So in eukarya, who is part of that VIP club? VIP club because that actually only happens 6 times in eukarya that we start, that we put together the building blocks that give you complex eukarya. So you have the animals, of course, but we're not the only one part of that VIP club. We share it with land plants, red algae, fungi, and kelp. Okay, so show some respect to kelp, because that's one of our exclusive cousins that tick the boxes of complex life. There gotta be a Donald Trump reference, right? All the American comedians are banking on him. I'm going to use him too. So I'm going to use him to talk about how do you get complex life forms. So the size of organism, of living organism, is a function of the amount of oxygen that you have around you. So if we take the present day, so quite high, highest, almost the highest in Earth's history, take high present-day oxygen level, actually, if you didn't have complex life form, if you only have organisms that move stuff around like oxygen by diffusion, the only time, the maximum size of organism would be a few millimeters. So yes, indeed, pretty much like Trump's hands. If you want something bigger, so I don't consider him as a complex life form, that's why. If you want bigger organism, you need other, you can't rely on diffusion anymore, you need other mechanisms to transport oxygen. For instance, in bilaterian animals, so bilaterian means with the right and left side, you need to develop things like respiratory and circulatory systems. So size matters, but so again, oxygen does too. So as you increase oxygen, so all right, so this is a sort of catch-22 process. You increase oxygen, so you increase the maximum size of organism you can get. Okay? And as you do that, as you get bigger organism, that means you could increase the surface to interior gradient of nutrients. Okay, you're going to have a big gradient concentration between the surface of the organism and the inside and the core of the organism. And that's actually important because that nutrient deprivation and that hypoxia, so that low oxygen inside the organism, that's important. That's going to help developing signals for cell differentiation. Okay, that's going to force the cell to find some ways to develop signals, so it's going to go around that nutrient deprivation. That nutrient gradient, that's going to also trigger a differentiation of the inside of the cell. And also, as you increase oxygen, you increase what we call oxidative stress. Oxidative stress is the bad guy by excellence because that's involved in many pathologies. In cancer, Parkinson's disease, Alzheimer's disease, all these guys, all these bad guys, now it's not like Trump, they involve oxidative stress. But in that case, it's actually, it's a bit of a shortcut, but that could be helpful because with oxidative stress, you produce what we call reactive oxygen species that induce cell differentiation. As we have cell differentiation, we're going to develop intercell communication, transport, so other ways to move stuff around, not just diffusion. So you can start having larger and more complex organisms. So then that's when it gets really interesting. And colleagues suggest, to look into journals that talk about plankton. Do we have any Kiwis in the room? They might not enjoy the joke. But there's a direct relationship between nutrient supply and the size of cells. And I put that in red because, again, that's going to be important. So when you have when you have nutrient-rich waters, that's where you can have large organisms, and even in the size distribution of different organisms, you can have actually large animals, like our beach whale, that can dominate the population. You guys know that video?
Yeah.
You gotta look it up if you don't on YouTube, beach whale. Because the beach eat plankton, boo. So that's me trying to use the accent. We'll come back to the beach whale actually towards the end. But nutrient supply is important, so that would have played an important role in the proterozoic with the development of complex life. That's going to be getting really bad for everyone because I'm going to start talking about genes. But I'll try to keep it short. So basically, when you look here at the tree of life for eukarya, so here we got metazoa, so that's our ancestors, so that's the start of animals, and Choanoflagellata is basically the closest cousin to animals. So the last guy before we started splitting into metazoan. And when we look at the different type of genes that you find in all these phylum, you find that actually some of them, so genes that express adhesion, cell signaling, they appear quite early into evolution. So yeah, we are what is called deuterostomia. What does that mean? I looked it up on Wikipedia. That means that the first opening during embryonic development is the anus. So think about that next time you speak out of your ass. That was the first thing that was developed during every deuterostomia organism, so including us. But in terms of genes, so some of the genes appear quite early, and you get things like NTP, PAX genes, so they already appear in porifera, so basically sponges. But it's not really complex yet. You really see a boost in the gene diversity, if you like, when you start dealing with eumetozoa. And eumetozoa start radiating, again, another important time, at around 650 million years. So around 650 million years, you see an increase in biodiversity, but also in terms of radiation, that's where you start seeing life forms that are starting to really show a complex gene pool and genes that's going to start doing all sorts of things. It's probably the last phylogenetic tree, thankfully. Otherwise, you're really going to wonder what I'm doing here. But just to make the point that most of the lineage in life was pretty much sketched out during the Proterozoic. Okay? So before the Cambrian explosion. During about 800 million years, which is the last common ancestor for animals, that's in the Cryogenian. Again, I promise I'm going to talk about that. And between that time and about 541 million years, so the end of the Proterozoic, we got most of the sketch of this tree that's established. From the Cambrian explosion onwards into the Phanerozoic, that's really the diversification at the phylum level. So that's where you start getting into the nitty-gritty of making different life forms. So finally, we're going to start looking at rocks. Okay, that's not going to be all about biology, but geology is going to help us. What happened with biology? So that's where we start looking at things like the Ediacaran, which is the youngest of the geologic curve. Not the youngest in its age, but the youngest that's recognized in stratigraphy that was established in 2004. So the most recent one that was established at the geological period. And that was defined actually, so the golden spike, so that thing used to recognize stratotype is in South Australia, it's in the Flinders Range, where a few of us are taking students next month, so it's going to be fun. And it also makes for some nice family picture with my mom. I am going to talk about my mom, so you guys are going to say, he's totally a mama's boy. I am, that's fine. But the Ediacara is going to be really interesting because that's going to look at that period of time where you after the Cryogenian, so in here, you actually already started making animals, and things are already going to be getting interesting in terms of evolution, diversification of life, before, of course, you hit the big guns of the Cambrian explosion. So in the Ediacara, so again, in terms of timeline for life, that's interesting, but also in terms of fossils, that's actually the first evidence so far, that might change, that we have of fossils of Metazoan. Mostly sort of footprints, if you like. It's in sandstone, and we didn't really have, or quartzite, we didn't really have skeleton of animals. But that's where we start. That's where we start having evidence in the fossil record of Metazoan. And also that's where we see, so that sort of genetic leap, that's diversification in genes between the choanoflagellates, so the cousins of the animals, and entering the animal kingdom, if you like. but things were actually still a little slow. And when in the early Ediacara, we still have organisms that are limited by diffusion. And as I explained, it's not very efficient things to move oxygen and nutrient around. It's only actually by the middle of the Ediacara that you have things like Kiberella, and then you start seeing developing a circulatory system. But again, it's key time for geology and for evolution. So, okay, so that's where actually we're going to get into where we can help with something, is to look at, well, what happened in terms of environmental change during the Ediacara. Okay, what happened on Earth that led to speed up evolution and start making complex life form. Interesting time, just before the Ediacara, you have, again, what is called the Cryogenian. Cryogenian, you get it, there's ice involved. So that's the last, what some people think, Earth-wide glaciation. Also times right after that, so during the Ediacara, we see high carbon burial that explains some of the stuff we see in carbon isotope, and a big increase, or probably the last big increase in oxygen. Yeah, so also, so you see I was talking about how the origin of animals is around 800 million years, but really evolution is speeding up at around 550, so it's a bit more than 200 million years of a gap. Again, there's not much happening. So why and how? So we have, so going back one step before the Ediacaran, we have the Cryogenian with, so possibly the Earth looks something like this, not something like that. That's just pure fantasy, but that would have been heaps of fun. Maybe they were involved. I mean, they were shooting down rebels, and maybe not. Maybe they were shooting down Eukarya too. But we have some glaciation, so some lasting longer than others. The Sturtian, which will be the longest one. Kaigas is less clear that it actually happened. Marinoan, so that's going to be a really interesting one, because that's just before Ediacara, so before things are getting interesting. And the Gaskiers, which is in the Ediacaran actually, it's not a Cryogenian anymore. Really short one, but in terms of evolution, actually could be a very interesting one, because that's right after that you really start seeing complex life. So, yeah, so we have basically this thing that what people, Paul Hoffman coined the term snowball Earth, and you get the idea. So what are the causes for snowball Earth? So one, there's a whole bunch of potential hypotheses. One of it, well, you had a lot of land mass, so you had Rodinia, so a supercontinent with a lot of land mass, and at the top here it's recent reconstruction near the equator. And as you put a continent in the tropics, it's hot, it's wet, you have a lot of chemical weathering that consume carbon dioxide, draw down the carbon dioxide, and that could lead to snowball Earth, to a really cool climate. We tested that actually recently with Nico. We had a little undergrad student project with Greg Briscoe, and they played looking at plate reconstruction and whether actually we had anything significant compared to the rest of the Proterozoic. Here, these bands, that's your snowball Earth event, and you can see, so for instance, that's two different plate reconstruction. That black curve, that's things being near the equator, and you see that, I mean, there is an increase here, but you didn't have more landmass in the equator, at the equator, than during the earlier part of the Neoproterozoic. So, yeah, probably not. Another hypothesis is the breakup of Rodinia. So again, you have this supercontinent, starts breaking up before the Cryogenian. So imagine big continents, think something like Siberia, where you have a lot of continentality. Okay, moisture can't get into the land, so you have really very little runoff, really dry supercontinent. very little chemical weathering. As you break up the supercontinents, you start making little continents that you have more coastline, if you like, more exposure to oceanic moisture. You increase runoff. As you increase runoff, you need water for weathering. So you increase weathering, that consumes carbon dioxide, that cools down the climate, that could be one of the drivers. And we did look at that. Well, that was mostly Greg and Nico, but I was happy to watch the results, and you do see an increase so quantification of the fragmentation was what they call breakup index, and you do see before the start of the Sturgeon glaciation, things are really breaking apart. So that could be one of the drivers, especially when you combine different latitudes in breakup index. You can see that compared to the Phanerozoic, okay, when you start breaking up Pangea, you also have, your breakup index that's increasing, but pretty much, different latitudes were all breaking up to about the same extent. What we have here in the Proterozoic is a little bit different. You see what's at high latitude is actually not breaking up that much, but the bigger effect was on the part of Rodinia that were at low latitude, that were near the equator. So you could have a combination of breaking up Rodinia, but breaking it up more where it matters for weathering and for CO2 drawdown. Another hypothesis, and they're not mutually exclusive. You can have, and most of the time that's the case, you have a combination of causes. Another possibility is the emplacement of large igneous provinces, lips. Because in that case, an example, the most recent example of that was the Deccan traps, 65 million years ago, probably one of the drivers for the extinction of dinosaurs. You pour out a lot of basalt, okay, so that's what's happening in Hawaii right now. It's really peanuts, okay? Think Hawaiian eruption on crack. Lots of basalt. The Franklin lip in Canada, that was just before the Sturgeon glaciation. We're talking about an area of 1 million square kilometers. So you pour out a lot of basalt. Basalt is really easy to dissolve, really easy to weather. So you do a lot of weathering, CO2 drawdown, and here we go, it's really cold. Another aspect, so it's more when we try to understand the carbon isotope record. Well, with weathering, there's phosphorus in the rock. That's actually the only place where the phosphorus is coming from. That means you put a lot of phosphorus in the ocean, drive the organic productivity up, increase carbon burial because stuff that lives eventually dies and is buried at the bottom of the ocean, which would explain the big spike we see in delta C13 in carbonates before the Sturgeon. So that's basically the fire and ice hypothesis. And if you didn't watch the Super Bowl, you don't get the joke. If you do watch the Super Bowl, that was a Super Bowl ad. It was very fun. Never mind, don't watch it. So then what happens? So okay, you start drawing down carbon dioxide, you start growing ice caps, and what's happening when your ice caps reach about 30 degrees latitude, so anything north and south of that, so here that would mean ice caps all the way to Coffs Harbour, you have what we call the albedo runaway effect, which basically means ice is reflecting heat, reflecting sunlight, sun energy. So that's gonna basically the system goes banana, like the minion is showing, and you're gonna just run even without any more forcing. You're just gonna grow more ice cap, and you might end up covering the entire planet with it. But during the Cryogenian, so that's all fine, it's covered in ice, The volcanoes are on a holiday, they're still working their butt off at releasing stuff from the inside of the planet. And with that, they release carbon dioxide and other form of greenhouse gases. So that builds up in the atmosphere, increases the temperature, and eventually that's how actually we don't stay forever into snowball Earth. You get a little bit of thawing and you get out of it. It's actually not that simple. If you have air-sea exchange during the snowball Earth, so meaning it's not completely frozen, you get a little bit of air getting into the water, that could slow down. The warming. So exit Hoth, enter Yavin, we go back to a greenhouse when finally life can prosper. Actually, not live long and prosper, that's another reference. Okay, so let's try to understand what's happening in terms of environmental change. And what we call cap carbonates, so this stack of rocks we see in the picture, they're going to be really helpful to understand that. They are archives of thawing. They were formed right after the end of this major glaciation. So one hypothesis is that how do they form? Well, you had, so the ice start melting, so you have melt water. That melt water is going to be really warm. We're actually talking 40, 60 degrees. Very acidic. That combined to dissolving carbonate platform that are now exposed. You remove the ice. Sea level is going to rise, but before that, they're exposed and they will dissolve very easily. So you have a massive flux of alkalinity into the ocean, which will drive precipitation of carbonates.
Hey Tony, you said we could interrupt. Why is the water so warm?
Because, well, remember we've been accumulating carbon dioxide in the atmosphere for a long time.
Mm.
So you're gonna get melt water. So not melt from the ice cap, pretty cold, but that's gonna be in contact with a super warm atmosphere.
Right. So people actually think the atmosphere went up to 40, 60 degrees essentially.
Well, I don't know the atmosphere, but they're talking about the water itself being 40, 60 degrees.
Okay.
So that's a bit of a hot bath.
So it's from very cold to very hot essentially.
Yeah, well, and that's actually how that maintains stratification in the ocean for quite a long time. So you got your ocean that's cold, that was trapped under ice, and you put on that very warm water. So that's how actually the melt water from the ice cap doesn't mix right away with the rest of the ocean. Another hypothesis is basically, well, with this low salinity melt water, you have conditions where you can have microbial activity and precipitation of those stones. And yet another hypothesis is the fact that as you remove the ice cap, you expose a whole bunch of sediment, and you have the release of what we call methane clathrate, so that we put a whole bunch of gas in the atmosphere, but also allow to dry the precipitation of carbonate. So that's where we're going to have fun looking at plots with wiggles and isotope. Isn't it nice? So what do we know about what happens when the snowbirds thaw? So people have been looking at a whole range of isotope proxies in these carbonates. What we learned from boron isotope that we see are decreasing, so that's the glaciation, and here you're in the carbonate. We see a decrease in delta 11, that's telling us ocean acidified. That makes sense. You got water that's becoming in contact with very high carbon dioxide in the atmosphere. That carbon dioxide dissolves in the water. That makes something even worse than Coca-Cola. Calcium isotope are telling us there was probably an increase in weathering fluxes from the continents, which you would expect. Suddenly you expose continents that have been ground by ice caps, so you have rock flowers, something really easy to weather. you should expect high weathering fluxes. But calcium isotope, that's not quite straightforward to explain. Then if you look at zinc isotope, we get a whole periodic table of them, so we might as well use them. What we see is first an increase in zinc isotope, which is telling us that actually right after the end of snowbirds, there's a resumption of primary productivity. Life kicks in right away, no delay. And that decrease is basically explained as you dilute that zinc with stuff that's coming from the continents. Triple oxygen, it's telling us something interesting, that we actually looking at the highest CO2 concentration in the atmosphere of the past 750 million years. Okay? So what we're doing right now, don't say that outside this room, but what we're doing right now to the atmosphere is really peanuts compared to what happened in the past. But in the past, at least you had millions of years to adapt to that. You know, we're doing things much, much faster, of course. And magnesium isotopes, so not in carbonate, but in silicate, so in the actual diamectite, so in the rocks from the glaciation before you start thawing. That increase in magnesium isotope is telling us, is suggesting that weathering actually start increasing before glaciation. Kind of weird. I don't really believe it. I work actually with the guy who published that, but that's fine. The other thing, looking at silicate, you're looking at something very local. So the advantage of looking at carbonates, they record the seawater composition, so you can have a much more global picture. But then, so what is happening in terms of nutrient supply? So who is feeding the fish when snowbirds thaw? It's so weird when you look up images on the internet. I'm just curious if that's actually something real. I can imagine that's only a problem men have. But yeah, let's not go any further. We can leave that for the UDBOC. So we need to understand, we need to better understand the continent inputs. Okay, what happened to the continents when you have deglaciation and you start supplying nutrients to the ocean? What really happened that triggered evolution once again? So what we need is a proxy for continental weathering, something that's really only, calcium might work a little bit, but that's ambiguous. That's something, we need a proxy that's only telling us about continental silicate weathering, and that's where Holly comes in. You want to keep that up? No? Okay. Lithium isotope. So lithium isotope that's been developed as quite a useful tool to look at this sort of question, because it's unequivocally, it's alright, doesn't matter, a proxy for silicate weathering. One of the cool things is that it's actually, the isotope composition in rocks is quite homogeneous. Whatever rock you look at, it's not very variable. That shoots around 0 or 2 or 2 per mil, between 0 and 2 per mil. In comparison, when you look at river water, you have a much wider range of values. So something's happening that is putting a lot of lithium-7 compared to 6 in the water. So why is that? I need beer. Well, that happens when rock gets dissolved. No, not the rock. A rock. So that's much better. I was so happy with that joke. I just love it. Okay, so to understand what's going on with lithium isotope, we need to look at what happens when you dissolve rocks, when you do chemical weathering. So you got lithium-6, lithium-7, and then you're going to partition these guys. So lithium-6 likes to be much better, not just in clays, but in secondary minerals in general. Clay, that can be iron oxide, all this sort of thing. Well, 7 likes to be in the water. So that's how you end up with a river water that's going to be rich in 7 compared to the starting point compared to the rock. And what's interesting is that that river, the composition of the river, is a function of the weathering regime. So what type of weathering you have on the continents in the catchment that that river is draining. So whether it's incongruent dissolution, as you often have in mountain ranges, or whether it's congruent dissolution, as you often have in tropical plains. So there you get the idea is that if you can go back in the past, that could tell you the sort of environment that you're looking at. And that's what people will do, where they look, for instance, in the Cenozoic, they look at the delta 7 in forams as a record of the composition of the seawater, which is going to be a function of the lithium that's supplied from the rivers to the ocean. And what they found is this, that curve here, you can see the delta 7 lithium increasing from the death of the dinosaurs until the present. So that's explained, so it's been quite debated, but that increase is explained as an increase in incongruent weathering, so a bigger role of mountain ranges on the supply of lithium to the ocean, and of course that's also a time of Himalayan uplift, so that could explain, so that Himalayan uplift could explain the lithium isotope record. But it's actually quite debated. Some people propose that that's nothing to do with the Himalaya. That's actually reflecting an increase, so not a change in the isotope ratio of the river, but a change in the flux of lithium from the river. So reflecting an increase in the dissolved lithium flux from the continent into the ocean. You have less lithium retaining clay, less clay formation, and as a result, so you have rivers with a heavier isotope composition. That could be a consequence, so less clay formation could be a consequence of a cooler climate. So that means Himalaya has nothing to do with driving this. That's just because it got cooler. So that's a consequence of the cooling, not the driver. So I should also say, well, we tried for decades to explain why the climate cooled during the Cenozoic. It's quite debated, and we thought lithium could help with that. And another possibility is that, well, that less clay formation is just because you have thinner soil, and that's where you bring back the mountains to explain that. You have more mountain range, you have more continent with thinner soil, which could explain why you would have less clay formation. So basically that means that the lithium isotope record, and in more general explaining why we have cooling during the Cenozoic, it's still a debate today. We're still looking for the proper explanation. But that's way too young for the topic of this seminar. So let's go back a little bit further in time. So another place, another part of the Earth's history where it's been applied, it's what we call Ocean Anoxic Event 2. So about 90 million years ago, that was basically really warm. That was a time of massive anoxia, so suddenly all the oxygen is gone. That means everything dies, high carbon burial, high CO2 and temperature, and possibly caused again by large igneous provinces, so by big volcanic eruption, in this case around Madagascar and the Caribbean. So at that time, that means, well, the Pliosaurus and Ichthyosaurus kaput, they're gone. That was before Chris Pratt came along. Can't imagine that's going to be a good movie, and saved all of them. But that was one of the cause for some of the extinction of some of the dinosaurs in the ocean. And what lithium isotope is showing us is that this decrease in delta 7 showing intense chemical weathering shortly after that event, shortly after that tragic event that's killing a lot of things, and where there's a lot of carbon dioxide. Well, that truckload of carbon dioxide is driving chemical weathering, which in turn regulates the carbon dioxide. So decrease in CO2 in the atmosphere, and quickly, actually, we go back to happy days, and Nemo can smile again. So back to the Flinders. Yes, Holly, I will embarrass you with pictures. So let's apply the lithium isotope to the part of the geologic record that we're interested in, the part that's telling us stuff happened in terms of evolution. So we quite happily go collect some rocks, and it can be quite fun smashing rocks, and you can see that we did very well with all the WHS requirements. But it's not just collecting rocks, there's also actually quite a fair bit of logistics involved in field work. So collecting wood for the campfire. I believe you are holding a beer in your mouth. Okay, but that's quite fun, and that's going to tell us actually some very interesting stuff. So then we bring these rocks back to the lab. You do ion exchange chromatography, separate the lithium that you then analyze on one of these big mass spectrometer that we have here. You need a mascot. Okay, so we have a wombat, of course. Jeff, the wombat. Protecting to get good analysis that works more or less. And then it's a shame that video is, oh yeah, it's working. So you need to keep the clean lab clean.
Is that TV?
That's Stevie at the back and Gabriel at the front. I found that video on the computer in the lab. I probably wasn't meant to find the video, but apparently that's what's happening. That wasn't late at night, okay? That was like 4:30. So at least they're not doing that in the middle of the night. They're quite thorough. I enjoy watching this. Anyway, so then that gives us some interesting results. So we apply that, actually we didn't just do that in South Australia. We also looked at the equivalent formation, cap carbonate in China, Dosseto formation. And that's sort of wiggles that we get. So at the bottom here, right before that you have the end, you have the glaciation. So the end of the glaciation is right here, and time is going up. And what you see, so in the cap carbonate, we start at quite a low isotope composition, and we'll see what that means in a minute. And then you have quite a rapid, well, we have quite a fair bit of variation, and that's actually going to be really important. So to go from carbonate to seawater, we need to understand what is the isotope fractionation between carbonate and seawater. So Holly and others, we did some precipitation. So with colleagues in Austria, we did some dolomite precipitation experiment. You do that at high temperature. It's very difficult actually to make dolomite, but that's a whole other question of geology. And that allows us to look at the relationship between isotope fractionation and temperature, and then use these to make an assumption on the temperature of the seawater in the Proterozoic, looking at the sort of translation to go from carbonate to seawater. And this is what we get, so that's these dots again, where you see the values here change. So that's what we think is the lithium isotope composition of the seawater in China and Australia back then. And we started values as low, so the modern seawater is at around 31 per mil. So we had times where we were something similar maybe to the modern ocean, but at the start, at the end of the glaciation, the start of the glaciation, actually we are quite low, down to about 23 per mil, which is equivalent to, in the Cenozoic, the Paleocene thermal maximum. So time of Earth's history that was really super warm, and we get the same sort of composition in the ocean. So really, really hot weather right at the start of the deglaciation, or at the start at least of the formation of the cap carbonate. So if you got data, you need a model. And we use a very simple box model to look at the variation of the lithium budget in the ocean and the isotope ratio of lithium in the ocean over time. as a function of basically what's coming from the river, so the flux and the ice-stock ratio, what's coming from hydrothermal inputs, so through the mid-ocean ridge into the ocean, and what's removed in the sediment. So as you have sediment at the bottom of the ocean, they will scavenge some lithium, and you have also some ice peak fractionation that is relatively well understood associated with that. So we can use all this to model how this flux and this ice-stock ratio from the rivers has changed over time. This shouldn't change. This is assumed constant for the lack of better constraint. That's not great, but that's just the way it is for now. So we're looking at how this changed over time. And we look at all sorts of scenarios, because when you start to publish that, people can be a real pain in the ass, so you really have to cover yourself and look at different scenarios. Because not everyone believes in snowball Earth, so we look at where we had a snowball Earth or slush ball, so where not the whole planet was covered in ice, there was some ice, so you still have some hydrology going on. We also look at different temperatures, so 10 or 40 degrees for the seawater. Delay or not between deglaciation and when you actually start making your carbonate, and also whether you have a well-mixed ocean or you have a stratified ocean. As I showed earlier, we have melt water eventually mixing with the rest of the ocean. And every time, there's only one way to reproduce the black curve, is basically the model reproducing the red and blue curve, which are polynomial fits through the data. You need a very large riverine flux of lithium, so a large flux of lithium from the continent for the whole duration of the carbonate. And in this case, we take a duration of about 3 million years. If you take anything shorter than that, as some people have suggested, you just can't reproduce these data. It's just impossible. But that means, so here what I highlighted, so FR, that's the ratio of the lithium flux compared to the modern one. So that means that we had lithium flux that were 20 to 40 times what they are today. And it's not just lithium you bring to the ocean, you bring all the other elements, so nutrients too. And we need change in the flux and also the ice-stock ratio that's coming from the river. And the only way we can reproduce the data is we have these different stages where the ice-stock ratio of the rivers that supply the ocean is changing on a time scale that's actually similar to Milankovitch cycles. So Milankovitch cycle, that's the signature of the Quaternary climate, was already kicking around possibly 650 million years ago. And that was actually probably the key to maintain this large flux of these nutrient of the ocean. Because you went from composition that would be low and that would tell you have intense weathering, so think tropical plains, to composition that tells you they are more significant of rivers that you have in Iceland, so where you have glacier breaking down rock. So that's the alternation of cold climate breaking down rock with periglacial processes, then warm climate dissolving all this broken down rock that probably sustain this large flux of nutrients into the ocean. So going back to our beach well brew, remember that at 650 million years, so pretty much the end of the Marino glaciation, more or less, you have that boost in biodiversity, you have radiation of Eumetozoan, the guys were really starting to get genetically complicated, and that's the time where we see that our beach well was probably loaded with nutrients, so very large nutrient supply. So that's actually going to be the end of it. Is it 8 o'clock yet? So then how do we make sense of that, of this large nutrient flux for 3 million years? What does that mean for evolution? So you turn around to evolutionary biology. So that was a paper actually suggested by my mom. Told you I'll talk about her. And they look at body size measurements. So we're not talking about old fossils, but also historical records. And what they see is that you do have rapid short-term evolution. Okay, it's not. Evolution is of course not static, especially when you have things like humans messing with species. They will drive artificial type of evolution, also island isolation, of course. But all these things, they don't result in major shift in evolution. Okay? This divergence in the genetic pool doesn't doesn't result in big shift in evolution. You need time for that. So what this graph is supposed to show is that, well, the divergence, regardless the time scale here, the divergence doesn't increase. It means you don't have a major shift in evolution. It does when you look at time scales that are greater than 1 million years. So the bottom line is that you do need sustained change in the environment, so for more than 1 million years to really drive evolution. And that's probably what happened in the Ediacaran, because that's what we see. We see that we had, for at least 3 million years, we had a massive nutrient supply to the ocean. And that was possibly sustained by Milankovitch's style climate variability. So, so was it the key, so that sustained nutrient supply, was it the key in this major evolution leap that we see during that period of time? So next, and we'll actually finish with that. So next, the thing would be to look at other parts of our history. So of course, the Cambrian explosion, also the Sturgeon glaciation. That's next for you, Holly. To look if we also see this link between sustained environmental change and major leap in evolution. So just to finish, just a reminder that yeast is our eukaryotic cousin. Okay, it's part of this VIP club of complex eukaryotes, so be nice to it. Thank you.